Alright guys, today we're going to go over total change. So before I talk about total change, it's probably not going to make a whole lot of sense why we're doing this unless we talk a little bit about where we're going in the course. So the first half of this course, we basically deal with derivatives. We learn a bunch of rules for computing derivatives, and we learn that derivatives tell us the derivative of a function tells us a whole bunch of stuff about a function. For example, the derivative of a function is the instantaneous rate of change of the function. It's the slope of a curve, which is, given by the function. So it's the limit of a difference quotient. That would look something like the limit as as h goes to 0 of f of x plus h minus f of x over h, right? So this is our difference quotient. It's the limit of that. And it's the opposite of an integral. So the second half of the course is what we're entering now, and in the second half of the course we talk about integrals. Basically, we're going to start constructing integrals today in the way that we constructed derivatives. Basically, we're going to start constructing integrals today in the way that we constructed derivatives in the early part of this course. So if you remember, we started the course talking just about difference quotients, and then we looked at the limits of difference quotients, and we said, that's this thing called derivative. It's equal to the slope of a curve, the rate of the change. So integrals represent exact total change in the same way that derivatives represent the exact instantaneous rate of change of a function. Integrals represent, they have a geometric interpretation, sort of similar to how derivatives have a geometric interpretation. So derivatives are the slope of a curve. Integrals tell you about the area under a curve. Integrals are defined by the limit of Riemann sums. So we're going to go over what is a Riemann sum today. And integrals are kind of sort of the opposite of derivatives. And so the relationship of integrals and derivatives is basically encapsulated by this formula here. This isn't actually a completely accurate formula. We'll go over that later. That lesson is called the fundamental theorem of calculus. But basically, the integral of a derivative is the function that you started with. So these two operations sort of cancel each other out. So today we're going to be talking about Riemann sums. Riemann sums approximate the areas under curves, and so that's what we're going to be using Riemann sums for today. They also approximate the total change that a function undergoes. So that's the other application that we're going to use them for. So basically, we're going to be interested for a while in just computing the areas, or approximately computing the areas under curves. So if I just wanted to look at the area under this curve, sine of x is this line. If I just wanted to look at the area under that curve between the points pi over 2 and pi, it looks something like this blue shaded region here. And we can approximate the area of this blue shaded region by computing the areas of a bunch of rectangles. And you might be asking yourself, well, geez, that looks like kind of a pain. Why would we want to do that if we could just find this region directly? And the answer is yes, this is kind of a pain, but this is also quite difficult to do in general. And so actually, in practice, it's often when computers compute integrals of fairly complicated functions, they're actually doing something like this internally anyway. So that's one good reason to look at this method, but the other method is that this is actually how this thing that we call integral is defined. And once we define this thing called integral, we'll be able to compute some of these areas exactly later in the course. So we're going to start with something really simple, which is that we're just going to approximate an area like that with one rectangle. So some of these problems are written in word problem type language. So I'll just give you an example of that now. Our example is find the total change in f of x, and the function f of x, between x equals 1 and x equals 2 if f prime of x equals 7. So here I've already gone and plotted the derivative f prime of x of our function. So I just want to show you what that rectangle would look like. So we're interested in the region between x equals 1 and x equals 2 on this graph. That would look something like this. Here's 1, here's 2. So this is the area we want to compute. That area is going to be, the base of this rectangle has length 1, right? 2 minus 1 is 1. And the height of this rectangle is 7. So the area is 7 times 2 minus 1, which is 7 times 1, which is 7. We can be exact in this case because, as you see, the rectangle matches the area underneath that part of the curve exactly, and that would be the answer to this problem. All right, here's a slightly more complicated problem. In this example, we've got a pot of water and it's heating up. Think about it, you got a big stock pot. You just put it on the stove with a bunch of water on it, and you're trying to warm it up, bring it up to a boil. The temperature of our pot of water is given by the function big T of t. Little t represents time. And this table gives us the rate of change of the temperature at various times. So the rate of change is, of course, the derivative, and that's what we have right here, right? T prime of t. And we start out at T prime of T is 4.2 kelvins per minute. And after 5 minutes, our rate of change has reduced somewhat to 3.9 kelvins per minute. We want to estimate the total change in the temperature of the pot on the time interval from 0 to 5 using the left-hand endpoint. So I'm just going to draw a graph of this situation, first of all. If we want to approximate the total change in the temperature based on the left-hand endpoint, that's this one, right? That's this endpoint. This is our left-hand endpoint of the interval, because this is the left-hand element of our interval. So we're going to basically we're approximating the total change in temperature, which is this area. And we're going to approximate that by computing the area of this rectangle. So this rectangle has length 5. It goes from the beginning of our interval at 0 here all the way over to 5. And the height of this rectangle is 4.2 kelvins per minute. So the basic idea here is if we were heating up at 4.2 kelvins per minute over a period of 5 minutes, the change in the temperature is approximately equal to 4.2 times 5 minutes. So that would be our answer. So that's our first estimate of the total change in temperature of this pot over that time interval. So then the next question is our answer from part A an overestimate or an underestimate of the actual change in temperature? And it's pretty easy to see from this graph that it is an overestimate, because we computed the area of the blue region, right? And the area of the blue region is definitely bigger than the area of the region underneath this curve. Moving on, there's another part of this question, which is the same two questions, but instead of computing left-hand endpoints, now we're computing right-hand endpoints. And then we're going to figure out if our example, or if our answer is still an overestimate or if it was an underestimate. So starting from the same graph, because we have the same data in our table, we want to approximate the area under this curve between times 0 and 5 by the right-hand endpoint of our interval. So that's this endpoint here, right? So this time we're going to compute the area of this rectangle, which has height 3.9 and width 5, right? So the area of the rectangle is 3.9 times 5, which is going to be 19.5 kelvins. And that is also the approximate total change of our temperature. Okay, and again, the question asks us, the problem asks us, is our answer an overestimate or an underestimate? And this time I think it's pretty clear. The actual rate of change would be given by this green area, which includes this little triangle up top. But we actually just computed the area of the blue rectangle, which is, it's less. It's strictly contained in that region. So in this case, our computation gave us an underestimate. All right, so that's that problem. Moving on. All right, so moving on, there's some other techniques that we can use to approximate the areas under curves. So first thing is the difference between left endpoints and right endpoints. So we've already seen that, but I'll just go ahead and draw some examples. So if we have the following derivative and we want to compute the total change in our function, we would first, using 4 intervals, and the left endpoint, we would start by drawing a line up from the baseline up to our curve, and dropping back down for our first rectangle, and then we would go up. And then same thing here. And so this is the left endpoint of my interval. This is my first interval. This is my second interval. This is my third interval. And this is my fourth interval. So again, the left endpoint of the interval touches the curve and then crosses over and comes back down, and that becomes my rectangle. And from here, the left endpoint of the interval comes up, touches the curve, crosses over, and comes back down. And here, the left interval comes up to the curve, crosses over, and comes back down. And so you can see starting to happen something that's a fairly typical situation for this type of problem, which is that some of these rectangles are underestimates. These two are underestimates, and some of these other rectangles here are overestimates. And so the upshot is that the overestimation and the underestimation kind of sort of cancel each other out, and they both grow small in the limit anyway. And so you can actually get some pretty accurate approximations of the region under these curves when you use enough rectangles. So it doesn't really seem that way when you're just doing one rectangle, but when you do multiple rectangles, you can get a pretty good approximation like this. So if we wanted to approximate the area under the same curve using right endpoints, that would look like the following thing. I would start from the right endpoint, draw the rectangle up until it touches the curve, and then cross over. And so that's well and fine as far as drawing graphs are concerned, but how do we actually approximate the change in the function from these graphs? Well, it's pretty simple. We've just got to set up a computation to compute the areas of these intervals, right? So the first point here on our axis, if I want to split up the interval from 0 to 2 into 4 subintervals, because that's what the problem tells me to do, I'm going to go from 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2, right? And that gives me 1, 2, 3, 4 intervals, right? 4 intervals, 4 rectangles. Since we're approximating based on left endpoints, the height of these rectangles, the height of the first rectangle is f prime of 0, right? So this height here is f prime of 0. And the base of this is 0.5 minus 0. So the base of length of this rectangle is 0.5, right? That's also equal to the total length of this divided by the number of intervals we're using. So 2 minus 0 over 4 is equal to 1/2 or 0.5. So that's the length of the base of our intervals, of our rectangles rather. So if I wanted to approximate the total change of my function between 0 and 2, I can see that as the area under this curve, and the area under this curve is approximately equal to 0.5 times f prime of 0. That's the area of the first rectangle. So I'll call that maybe R1. The area of my second rectangle is 0.5 because the base still has length 0.5, and the height of this rectangle is f prime of 0.5. So that's my R2. And then I've got two more terms here. 0.5 times f prime of 1. So f prime of 1 is this height right here, and this is 0.5 again. So this will be R3. Plus 0.5 times f prime of 1.5. And this would be the area of the rectangle R4, which is right here. So again, this height here is f prime of 1.5. This height here was f prime of 1. And the length of this rectangle is 0.5. Putting all of those terms together, this is my approximation of the area under my curve. And so sometimes we can write that in a more compact notation because we've got the same factor of 0.5 everywhere. So this is 0.5 times f prime of 0 plus f prime of 0.5 plus f prime of 1 plus f prime of 1.5. Right. Okay, so similarly, we can do something similar over here. So the height of our first rectangle, so again, we split up into the same 4 intervals. So the height of our first rectangle, R1, is going to be f prime of 0.5 this time. And the length of the intervals is all the same. They're all still 0.5. So the upshot is I'm going to end up with a different sum here. And instead of the height of my first rectangle being f prime of 0, the height of my first rectangle is going to be f prime of 0.5. But otherwise, the formula is going to be the same. So you can write it out this way if you want to. But the upshot is that you're going to get the following formula. It'll be f prime of 0.5 plus f prime of 1 plus f prime of 1.5 plus f prime of 2, right? And where does that come from? Well, the height of the last rectangle is f prime of 2. The height of the second to last rectangle is f prime of 1.5. And the height of the third from last rectangle will be f prime of 1. And then the height of the fourth from last, which is also the first rectangle, would be f prime of 0.5. So each of these things in each of these terms ends up down here, and then each of the intervals has the same length, so we just multiply the whole thing by 0.5. All right, so that's a pretty typical Riemann sum calculation. These can get really ugly, as we'll see. Eventually, you might have to compute 20 or more terms for something like this in order to get an accurate enough approximation to some functions. So that's kind of a difficult situation. There's not a whole lot we can do about that to make it easier. Calculator is definitely your friend for these types of problems. A little bit later in the course, we'll have the ability to check our work sometimes for these problems by actually computing the exact area under the curve by computing an integral. But integrals are not easy to compute in general. So for some problems, this type of technique is necessary, unfortunately. So there's a couple more techniques that we can use to approximate the area under the curve. So I just want to give you guys an indication of what those look like now. So the next technique is called midpoints. So instead of using the left or right boundary of our interval to draw our rectangles, we're going to use the midpoint. And what that looks like is the following things. Instead of coming up from here to draw my rectangle, that would be the left rectangle. Or coming up from here to draw my rectangle, that would be the right rectangle. I'm going to use the midpoint of my interval. So my first interval is from 0 to 0.5. So I'll just come over here, and then I'll go out in both directions, and then come back down. And that will be my first rectangle in my Riemann sum. So R1. And then my second rectangle, same thing. I'll start at the midpoint of this interval. I'll go all the way up, and then I'll hit the curve, and then I'll spread out, and then I'll go back down. As you can see, this gives a nice approximation. It's a little bit overestimating here. It's a little bit underestimating here. So this it's a pretty good accurate estimation of the actual area under the curve. Oops. It might be good for some functions. There's probably going to be some functions for which this technique will fail to be accurate. You could specifically construct a function to be ugly enough that this thing is not super accurate, but basically in the limit, as we take sufficiently many rectangles, we've only done 4 rectangles here, but I think you can see if you did 40 rectangles or 400 rectangles, you would get a pretty good approximation to the actual area under this curve, even if your function did something really goofy like this. If my function was like this, then the midpoint rule would give me these rectangles, and it would be not a very good estimate of my function. But if I then did 40 rectangles, then I would fill up those gaps underneath those curves there, and I would get a pretty good approximation again. So how do we compute a Riemann sum or approximate the area under a curve or the total change using the midpoints of the rectangles? It's pretty simple. Again, we just multiply the length of each rectangle, and instead of if we wanted the left endpoint of R1, we would do f prime of 0 because that's this point here. That would be the length, the height of this side. If we wanted the right endpoint, we would do f prime of 0.5 because that would be the right side of this first rectangle here. But we don't want either of those. We want the midpoint, right? So that would be 0.25. 0.25 is halfway between 0 and 0.5. So this is 0.25 here. So this height here is given by f prime of 0.25, and therefore the area of the rectangle is the width of the base times the height. So base times height, base in this case is 0.5, height is f prime of 0.25. And so that gives us our height of our first rectangle. So that's R1. And then the height of the second rectangle is going to be f prime of, it's halfway between 0.5 and 1, so f prime is 0.75. So this is our base. This is our height of R1. This is our R2 height, our height of R2. R2 is this rectangle. R3 and R4 are those rectangles. And so the last two terms would be f prime of 1.25. That would be our height of R3. And f prime of 1.75, that would be our height of R4. So the area of each rectangle is base times height. If we add all those up and then we factor out the base term because it's the same, so we might as well, then we end up with this formula. Okay. So that's how we would approximate the total change based on midpoints. There's a fair amount of problems like that you'll be doing this semester. The last one is the least common. Apart from, there are some advanced techniques like Simpson's rule and stuff that we don't cover in this course, but just FYI, there are more advanced techniques out there that you might find on Google. But so the next technique is called the trapezoid rule, or using trapezoids. So the basic idea is, instead of going up from just the left, just the right, or just the middle and drawing an appropriate rectangle to approximate the area under the curve, what we're going to do instead is At each interval, we're actually going to go up from the left, and then we're also going to go up from the right, and that's going to touch the curve at 2 different points. And then we're going to draw a little straight line in between the 2 points where our blue lines touch the curve, and then we're going to compute this area. And this area is, this shaded region that I've just shaded here is a trapezoid. You know, it kind of doesn't, might not look like one at first glance, but if you rotate it, you'll see that it's a region like this, which is a trapezoid. So the height of the left-hand side is f prime of 0. The height of the right-hand side is f prime of 0.5. The base here is 0.5. And so the area of that trapezoid, that first trapezoid, is 0.5 times the average of the 2 heights. So times 1/2, rather maybe I should factor that out, f prime of 0 plus f prime of 0.5 over 2, right? So that's the area of that trapezoid, and I'll call that trapezoid T1. So that's the area of T1. And then we can do that 4 more times, and we'll end up with some trapezoids that look like this. And so you can see that this, it does a really nice job of hugging the contours of the curve. And so it's going to give us a pretty nice, accurate approximation for the area under the curve. The only real downside of this method is that it's hard to compute by hand accurately because you've got uglier terms. So, but the upshot is, I'll just go ahead and write the rest of the terms now. So the area of the second trapezoid would be 0.5 times f prime of 0.5 plus f prime of 1 over 2. The area of the third trapezoid would be 0.5. They all have the same base, so we're getting 0.5 everywhere again. F prime of 1 plus f prime of 1.5 over 2. And the area of the last trapezoid would be 0.5 times f prime of 1.5 plus f prime of 2 all over 2. Now you can do some algebraic tricks with this, which they might actually find, they might make the formula a little bit easier to compute or a little bit harder to compute for you. So I'll go over those briefly, just to give you an idea in case you see those while studying. You'll commonly find these algebraic tricks in textbooks and the like, but it's not really necessary to use these tricks. Basically, what we've done so far here is already correct. Like, this is enough to compute to finish the problem. So this problem is impossible to finish, I guess, because the problem didn't actually tell us what f prime was. But if it did, then we would just if f prime was equal to x squared or something, then we would just compute 0 squared, 0.5 squared, 0.5 squared, 1 squared, etc., and we could finish this thing. But so the first thing we can do here, that's kind of a funny trick, is we can pull out the 0.5, and we've been doing that before. And actually, we can pull out a factor of 2 also. So really what we've got is 0.25 times f prime of 0 plus f prime of 0.5 plus f prime of 0.5 plus f prime of 1 plus f prime of 1 plus f prime of 1.5 plus f prime of 1.5 plus f prime of 2. And that looks kind of weird, but I promise it's accurate. Like f prime of 0 plus f prime of 1.5, that came from here. F prime of 0.5 plus f prime of 1, that came from here. F prime of 1 plus f prime of 1.5, that came from here. And the last term, f prime of 1.5 plus f prime of 2, came from here. So every term is accounted for, and this formula does check out. But I just wanted to draw your attention to the fact that this actually simplifies, right? We've got f prime of 0.5 in there twice. We've got f prime of 1 in there twice. So this is really f prime of 0 plus 2 f prime of 0.5 plus 2 f prime of 1 plus 2 f prime of 1.5 plus f prime of 2. So this is the formula that you'll commonly find in textbooks for the trapezoidal rule. So it's and it is accurate, and it is the same trapezoidal rule as this formula is. Okay, so I think we have time for one more example. So let's do that. So our example says the velocity of an object is given by v of t equals 1 plus t squared, and the example asks us to estimate the total distance traveled by the object over the interval from 0 to 4 using 8 intervals and the midpoints, and then using enough intervals to get 1 decimal point of accuracy. So we'll start by using 8 intervals and the midpoints. So let me just sketch the situation. Okay, so our velocity function looks something like this. It starts at 1, and then it grows according to t squared. We're only interested in the interval from 0 to 4. We're going to split it up into 8 intervals, so 2, 3, 4, 5, 6, 7. Really? Yeah. All right, I'm going to redraw those. Okay, so that would be 2 intervals, that would be 4 intervals, and that would be 8 intervals. Looks nice. 2, 1, 3. All right, so the area under this curve is approximately something like this. Okay, so the problem asks us to use 8 intervals. We've drawn those, and it asks us to use midpoints. So the area under this curve is approximately something like this. So using the midpoint formula, we would find that the approximate change in f is, well, each interval here has length 0.5. So it would be 0.5, and then I need to find the midpoints of all these intervals. So the first interval is from 0 to 0.5. So the midpoint would be 0.25. The next interval would be from 0.5 to 1, so then I would get 0.75, whoops, f prime, and then I'll just go ahead and compute the rest of those. So the upshot is the distance traveled is approximately 50.5. All right, the second part of the problem asks us to use enough intervals to get 1 decimal point of accuracy. So this is the sort of thing where this type of problem gets difficult and annoying. Basically, we need to just keep computing larger and larger numbers of intervals until our answers converge to something, until our answer stops changing. So, for example, another approximation to this that would use 16 intervals would look like the following. And so, obviously, a computer or a calculator is your friend for problems like this. And I'm sorry, I just found an error up here. So I had forgotten to multiply by this leading constant of 0.5. So the actual answer is closer to 25.25. And as for this one, with 16 intervals, we get 25.3125. And if we used more intervals, we would get more. But as you can see, that we're already within 1 decimal point of accuracy, right? Because if I round this, that's approximately 25.3. And this one rounded is also approximately 25.3. So this is called convergence, when our numerical approximations stop changing. So at that point, we know that we're at least 1 decimal point accurate, and that's all the problem asked for, so we are done.